We're going to be talking about gas laws, guys. Gas laws are actually really, really relatable to everyday life, especially this time of year. All right, when it's so cold out, and as we get into springtime, especially up here when, the days are warmer and the nighttime is colder, right? There's something that we use every day that you got to think about, and that's your tires, okay? The air pressure within your tires, and seeing how that's related. Has anybody ever woken up in the morning and you go outside and you see, like, in the wintertime, maybe it looks like you have a flat tire, but the night before it was perfectly fine looking? Have you ever noticed that before? You don't have cars, but your parents do, right? You ride around in them. Maybe not the tire on a car, but a basketball. Okay. In the wintertime, if you got to shoot on a nice day, if you got a hoop outside, it might be flat, where it was fine the day before. Well, that's related to temperature and pressure. We're going to see kind of how those pieces play apart. So pressure, guys, our variable for that is going to be a capital P, capital V for volume, capital T for temperature. When we see N, okay, N means number of moles. So for here on out, the rest of the school year, if you see a lowercase n, it's talking about the number of moles. We're going to utilize this with the ideal gas law, which is something you're going to have to memorize. Now, on our table T, we have a few of these gas laws. We have what's called the combined gas law, but nothing else. So we're going to add it in there to hopefully have you guys memorize it. It's actually a really easy formula to memorize, that ideal gas law. It's something that we use a whole lot. I have a song as well that we're going to get to hear, which will hopefully help you remember that. Stoichiometry is going to be coming back as well, volume stoichiometry. So a lot of review here going on in this unit. So the three gas laws, guys, they're the basic ones that we call, and then we kind of have the combined gas law that goes with that, and then the ideal gas law that we're going to talk about as well. So we're going to just kind of jump right in. The first law is Boyles Law. This is a picture of Robert Boyle. He was the one who developed this. This is the law, guys, that relates volume and pressure and volume. So our formula for that is P1V1 equals P2V2. Right? If you take a look at that, P1V1 equals P2V2, what type of relationship? All right, so that's the idea we want to think about within all of these. What's the relationship between pressure and volume? So think about this. You've got pressure and volume that are being multiplied together. All right, so if this goes up, what does the volume have to do to keep it equal to each other? It's got to go down. What type of relationship is that? Indirect, guys. Or what's another term for indirect?
Inverse.
Yeah, inverse relationship. That's the type of relationship that Boyle's Law looks at. Okay, indirect versus inverse, or not versus, same, indirect / inverse. Temperature, notice, guys, remains constant. So this formula does not use temperature at all. Fun fact of the day: he influenced Isaac Newton. Right? He came around before Isaac Newton. You've all heard about that. So our graph, that's one thing you want to be able to look at, guys. An inverse relationship graph. As pressure goes up over here, when we look at our graph, pressure gets up, what happens to the volume? Volume gets smaller as we get higher in pressure. And then the opposite is true as well. As volume increases, pressure goes down. All right, so I've got a video clip that I'm going to show you guys to illustrate. Here's our example, okay? This is where it becomes vital, guys, that you record the information. Those of you who have been too lazy to write down and identify the pieces that you're given, this unit, more than any other unit, is going to be a challenge because there's so many different pieces. We're going to have like 5 or 6 variables within one equation. You've got to keep them all in order. So here we go. What are we given? When we read this, it says, if 1 liter of a gas at 1.2 atmospheres is allowed to expand to 5 liters, what is the new pressure? So what's one piece of information we're given? Which is what, though? Volume. Now, the whole idea here is we have volume equals 1.0 liters, and then the key word, guys, is at what? Right, so there's our pressure, 1.2 atm. So by using that keyword at, that's saying that, hey, these two variables go together. We're going to call them P1 and V1. All right? We could call them P2 and V2. It doesn't matter as long as we are saying that, hey, these two go together. They're the same set of variables. Does that make sense? You tracking with what I'm saying? Okay? They go together. You've got a volume at this condition, or you've got a pressure at this volume. All right? They go together. And then we also have V2, 5.0 liters. So what are we looking for? P2. So we don't have any temperature given to us, so we know we're going to use P1 V1 equals P2 V2, and I encourage you guys, move your equation, move your variables around first before you plug in numbers. All right? Get your unknown by itself. We're trying to get P2 by itself, so I'm going to divide by V2 from both sides. So my new formula is P2 equals P1 V1 all over V2. Now it's just plug and chug. P1, 1.2 ATM, multiplied by V1, which is 1.0 liters. That's easy math. Divided by 5.0 liters. Liters will cancel out. My P2, my unit's going to be atmospheres, which is a good pressure unit. Go ahead and do the math. Yeah. 0.24 ATM. Sig figs. We want to make sure, I'm going to try to remember to remind you guys, sig figs all throughout this unit. Okay? Is this really that difficult? No, this is simple math. We've done stuff a lot harder. The hardest part, guys, is once we get all 6 or 7 or 8 equations, it's identifying which equation to use. That's the hardest part in this unit. Okay? All right. You guys go ahead and try this problem. When you start plugging in values before you solve for your unknown, and you have to rearrange it anyway, numbers get mixed up, units get lost, so it's just a good strategy to get it like this first, then plug in the numbers. All right, you obviously have the choice of how you want to do it. I'm just trying to encourage you guys to be as streamlined as possible. All right, so plug in all those values that we wrote down. Cross them out. Milliliters will be our unit, which is a good volume unit. 720 times 150 divided by 750. How many sig figs should we report our final answer to? No, 2. 2. Because they all have 2 sig figs in there. There's no decimal, so that 0 is not significant. So, what's our answer without it being rounded? 144 milliliters. So when we round it to correct sig figs, 140 milliliters. Does it? That's Boyles Law. Let's talk about Charles' Law as the next one. All right? It was developed by the French scientist Jacques Charlet. No, there's no French here at this school, is there? Charlet? Charles? I don't know how you say it. I never took French. Franish. I took Spanish. All right? It's been a long time. All right. What's that? I mean, okay, and that's why if you look in your reference packet, you don't actually have all the individual laws written out there. They're all combined, okay? So it's really all of these pieces playing a part. I'll teach you guys in a little bit how we utilize that for what we need. So we have, these are fractions here. It's really V1 over T1 equals V2 over T2. Now, if you think back to Boyles' Law, guys, that was an inverse relationship. Is this set up the same way as Boyles' Law mathematically? No, now we have fractions, right? So what do you think that's going to do to the relationship? If one goes up, the other one's going to do what? Yeah, it's going to go up as well. It's a direct relationship, guys, and this is what the graph looks like. I want you in your notes to be jotting down these graphs off to the side so that you can identify them in case they ask you which graph shows the relationship between pressure and temperature or pressure and volume on your Regents exam. Those are common questions that they could ask. All right, and then you can actually look at the formulas and do some math to kind of help you with it, but if you can kind of remember it, it's going to make it a little bit easier. Why do you think I have in big, bold letters that T must be in Kelvin? Why do you think I have it there that the temperature must be in Kelvin? Okay, it's very important. But why? What's so important, guys, or unique about the Kelvin scale that we talked about in our last unit? Alex?
It's like the same scale as Celsius, but it's starting at absolute 0.
Okay, so it's the same increments as Celsius. They change by the same amount. 10 degrees Celsius is 10 degrees Kelvin. And then it starts at absolute 0. Well, what's absolute 0 again?
It's the lowest possible. Oh, it's when particles stop.
Right, particles stop. It's the lowest possible temperature. So what do you think is so important about using Kelvin here then? Since it starts at 0, it means it can't be a what? It can't be a negative number, guys. If you had a negative value there for your temperatures, that means you could get a negative volume potentially. Can you have a negative volume? No. That's why temperature must be in Kelvin, because you can't have a negative volume. All right? You got to keep this in mind. So with that, you've got to know how to convert between Celsius and Kelvin. If you look at Table T on your reference packet, you actually have the formula given to you to show you how to go between those.
It's so much easier.
All right? Here. So if we take a look, this is how they're related. Take your degrees Celsius, you add 273. If you're trying to do the opposite, to go from Kelvin back to Celsius, guys, you subtract 273, okay? Solve for your unknown. You guys can do this. We're not going to spend a lot of time with it. Bless you. All right, let's jump into an example. Yes, I have the answer there. We want to make sure the answer is going to be correct. So it says a helium balloon, helium-filled balloon has a volume. There we go. Jot it down. V1 equals 2.75 liters at 20 degrees Celsius. Now, my encouragement to you all, and every year I encourage my students, is when you see something in Celsius, immediately convert it to Kelvin. Don't wait until you start working the problem because it's so easy to forget. And I speak from experience. I cannot tell you how many times I have forgotten to convert to Kelvin and I've got something wrong. I did everything correctly, but I got it wrong because I didn't do it, have it in the right temperature scale. So to go from Celsius to Kelvin, we add 273. So that means this is going to be 293 K. All right, that's taken care of. The volume of the balloon decreases to 2.46 liters. So V2 equals 2.46 liters. If it is placed outside in a cold day, what is the outside temperature? So this right here, guys, is why if you look at your basketball in the wintertime, on one day it's one volume, it's pumped up, it's got enough air in it. The next day, if it's really cold, it might be flat. Or if you look on a car tire, you go outside, your tire looks a little flat because it's gotten so cold. Let's talk about why. Why is this happening? Alex? Absolutely, guys. That's why we did that unit first, is so that now this makes sense. Those particles get cooled down so they start moving slower, which is going to change the volume. All right, so let's go ahead and just go ahead and solve through this. We've got V1 over T1. Now, this formula, it becomes imperative, guys, that you really think about what's going on. We've got fractions here. Fractions where people start to struggle. What's the easiest way to clear a fraction?
Multiply by itself.
Or cross multiply, which is the same thing, multiplying by itself. But guys, cross multiply. So rewrite a new formula. We now have V1 T2 equals T1 V2. Does it matter what order I put these in my new formula? Whether it's T first or V first? No, because it's multiplication.
Why didn't they just make that before?
Because that doesn't show that it's that direct or indirect relationship. By having it with the fractions, it's showing you the direct relationship. All right, so now solve for your unknown. We're looking for T2. All right, so we're going to get that by itself. We're going to divide by V1. Bam. So we have T2 equals T1 V2 over V1. It's very easy to make mistakes. This is why, again, I'm trying to encourage you guys to solve for your unknown first so that now it's just plug and chug if you have things written down. This is where things get a little hazy if you start going too quickly. All right, so here we go. Plug it in. We got 293K multiplied by 2.4 liters, V2, all over 2.75 liters. And again, since we have multiple pieces, it's important if you write them down like we did right here, it can make this part down here a whole lot easier. 262 Kelvin. Now let's think about it. Does our answer make sense? We know that this is a what type of relationship here?
Direct.
It's direct. So that means if we take a look, guys, V1 went from 2.75 liters down to 2.46, so it went down. What should our temperature then do if it's a direct relationship? Did it go down 293 to 262? Absolutely. So you've got a little built-in check if you can remember what the relationships are like with these simple ones to know what's going on. So this is what you should have, and then when you do the math, guys, 815 mils is what you should end up with. Think about it. You can ask yourself, does my answer make sense? My temperature did what? It went up, so what should my volume do here? It should go up as well. The other one, which one? Charles, guys. Very, very similar to Charles. So what type of relationship is this then? It's a direct relationship as well. Okay. So what's the graph going to look like for this? Pressure, temperature. What's it going to look like? Yeah. What did it look like? Linear line that was constantly increasing. Okay. That's as straight as I can make it. So now instead of talking about volume and temperature, guys, it's pressure and temperature. So this is where that first video I showed you is kind of a mix of this as well as Boyles Law. So you guys are going to work the next problem in your notes. This is the bigger one that we're going to talk about more. This is the formula that is actually in Table T on your reference page. So everybody look at Table T right now. It's toward the bottom. So if you look, they label the variables for you. Pressure, temperature, and volume. You have this formula. Now, with this combined gas law formula, you can get any of the other three that we've already talked about because they're all in one. All you have to do is cover up the pieces you don't need. So let's say you're given pressure and volume but not temperature. Well, you just cover up the two temperatures there, and then you have Boyles Law. If you are given volume and temperature only, what you can do then is you just cover up the pressures. There's Charles' Law. And then right here, if you covered up volume, there's your gay-lussac's law. So either way, you have all the ones that you need. You use the parts that you're given to then solve for whatever variable you're looking for. All right, so here's our example. This is where it becomes very important that you actually write down all of the variables first. And the way I grade, I will give you a point for writing the variables down. Even if you don't know how to do anything else from there, you need at least a point for writing those down and defining them correctly. 282.4 milliliters. What variable is that? V1. Of a gas at 25 degrees Celsius, that's going to be my T1. Now, what do I need to do with that? Yeah, go right to Kelvin with it. So that's going to be 298 Kelvin and 1.3 atmospheres. So there's my P1. Is cool. There's your terminology, guys. There's the change. So up until this point, all of this data right here goes together. Whether we call it P1, V1, and T1, or P2, V2, and T2, they all go together. They all have the same subscript number. Okay? It's cool to our new conditions. So T2 equals 20 degrees Celsius. Add 273 to it. We get 293 Kelvin. And 750 millimeters mercury. Oh boy. What do we have to do with that pressure?
Divided by 760.
Or what else could we do? Do we have to have it?
1.3.
Right. Either way, me personally, I like to get to atmospheres just because it's smaller. All right, smaller numbers to deal with. So divide that by 760. What do we get? 1.02 atmospheres. And then we're looking for V2. Okay. So we got P1 V1 over T1 equals P2 V2 over T2. We need to get V2 by itself. So again, cross multiply. That's the first thing, guys. Clear your fractions out. So we get P1 V1 T2 equals P2 V2 T1. Now you can solve and rearrange for your unknown variable. We need to get V2 by itself. Now it's just plug and chug. So we got 1.3 ATM times 282.4 milliliters times T2, which we said was 293 Kelvin. P2 is 1.02 ATM. And T1 is going to be 298 Kelvin. So Kelvin temperature units going to cancel out. So our pressure units, V2 equals... Do the math. We're not talking about Dwight here. We're talking about our volume, Alex. Alex is going to tell us the volume for this problem, where Boyles was indirect, Charles and gay-lussacs were direct. This one, it's not as simple as that because you got kind of everything combined together, so it's not just as simple. So when you go ahead and do the math, 101.3 kPa times 700 times 303 divided by 200 divided by 273, what do we get for our second pressure? What'd you say?
394.
Does anybody else get that? 394 kPa. All right, so there's a lot of moving pieces. The more organized you can be, the easier it is for you. Okay, you want to take those steps to kind of go through all that stuff. All right, that's as far as we're going to go today, guys. We've went through the basic ones up through the combined gas law. Hang on. Guys, Dalton's law of partial pressure is pretty simple. Okay. Basically, it's just the pressure of each gas in a mixture. So you've got a mixture of gases like in this room right now. Each gas has its own pressure that adds up to the entire atmospheric pressure. So like nitrogen would have a pressure, carbon dioxide, water vapor would, oxygen would, and they all make up the total pressure in this room. So it's the sum of all the partial pressures. Most cases, you just take your total pressure, or notice it says atmospheric pressure, and it's the pressure of gas 1 plus the pressure of gas 2 until you run out of all the gases. So you just basically add them up, okay? A special case, though, is where gases are collected by water displacement. So if they gave you a problem like this on the reading exam, which I don't know if they're going to or not, they would have to give you this table that I'm talking about here. Right? We don't have it. I'm going to give you guys that reference material later for the problems that you're going to need on your homework. Okay? So they have to give you that. You're not going to have to memorize all of those. But the same thing would just be true. You just take out the water pressure, the pressure of the water vapor, and then you're left with the pressure of your gas. When we do our lab later this week, where we're going to figure out the molar mass of the stuff that's in the lighters, in the lighter fluid, we will have to use this method right here. All right, so here's an example. Okay, the barometric pressure of a temperature are 84.5 kPa and 20 degrees Celsius. We need to figure out the partial pressure of oxygen. So we have our total pressure, or ATM, equals 84.5 kPa. Right? We're looking for the partial pressure of the oxygen gas. Well, there's going to be some partial pressure of water vapor because it's collected by water displacement. What is water doing, guys, all the time when it's in the liquid state? All the time. Moving, okay. But think about our last unit when we talked about liquids are always doing what? Evaporating. What does evaporating mean? Well, it's going from a liquid to a gas. So when you collect something over water, typically in labs, when they're doing reactions, they will bubble gases through water to collect it. All right, it's the best way to do that. We're going to do that, like I said, on Friday with our lab that we're going to do. All right. But the water vapor is evaporating all the time, so that's going to play a partial role within that. So I'm going to look that up here in a second. Basically, you're given the temperature not for any part of the calculation, but to get the value for the water vapor, all right, at that given temperature. 2.3 kPa. So guys, here we go. We have our P total equals the pressure of gas 1 plus the pressure of gas 2. So we're looking for the pressure of oxygen gas, and this is H2O. Well, get oxygen by itself. Okay, so it's going to be PT minus P of the H2O. Our total pressure is 84.5 kPa minus that 2.3 kPa, which was the partial pressure of the water. That's simple. Partial pressure, guys, is super, super easy. You just add them all up, or you subtract out the ones from the total, looking for the missing one. All right? Any questions?